Let's talk about sketching graphs, our relations, our functions. Why is this important? Well, look, it's all about data, isn't it? And once you've gathered data, you want to present it. And often we'll do it in a graph. That way, when we see the picture, we can pick up patterns that might exist between the data. The type of pattern determined by the shape of the data. Straight line, linear function, and so on. If it can be approximated by a known function, then great. Analysis of that data becomes real easy because we can just get the equation of that function and sub information in, make predictions and so on. This is why it's important that when you plot data, your scale needs to be consistent. That doesn't necessarily mean you have to have the same scale on both the vertical and the horizontal, but a scale itself has to be consistent. Otherwise, you might bring yourself to a wrong conclusion. Known functions can be sketched very easily. These pieces of information can be easy to find. Y-intercepts, of course, very easy to find. X equals 0. X-intercepts, sometimes are not that easy to find depending on the equation, but we want to solve the equation equals 0. But once we've got the intercepts, if we know the basic shape of the curve, then getting a sketch is relatively easy. Specific features unique to a type of function can be determined by just looking at the equation. And of course, don't forget the basic idea which goes back to year 7, maybe even before that. Table of values. If you're unsure, just plot values to get a feel for what the curve's doing. Let's start with our linear function. And the most basic linear function of them all, y equals x. Linear function with our data means it has a direct variation. As one goes up, the other goes up, and one goes down, the other goes down. So yes, we call it the linear function because it's a line. Line of best fits. Right? That's what we use with data, in experiments and what have you. If we can draw a line of best fit in there, again, we can come up with an equation of a line and make predictions. We can interpolate or extrapolate depending on what we're doing with the data. But all straight lines can be transformed from that basic equation y equals x via different transformations. Translation, rotation, reflection, or it might be a dilation. But you can recreate every straight line out of the basic one, y equals x. And of course, how do we recognize it? Well, you might recall this little thing, y equals mx plus b. That's how we look at them, and we notice, oh, look at this. The power of both the dependent and the independent variable is 1. That's when we know we've got a linear function. And when it is expressed with y being the subject, then we know that, hey, the coefficient of x is the slope and the constant is the y-intercept. There's some of the basic ideas with linear functions. But there are, of course, a couple of special linear functions. One that is parallel to the x-axis, so a horizontal line. And let's imagine that one goes through the point 3, 2. It would simply have the equation y equals 2. It still satisfies y equals mx plus b. It just means the slope is 0. It still satisfies it. But every single point on that line would have a y value of 2. And then, of course, we've got the vertical ones that are parallel to the y-axis, and that would be x equals a constant number. And if that went through 3, 2, we'd get x equals 3. We're going to show that the point 2,4 lies on the line x plus y equals 6. Not a really difficult question, but I use it to illustrate something here. Show that question. Show that questions are not necessarily proving something, it's just showing something. And it's perfectly legitimate to substitute in the given information and show that it works. It's show that. So all I have to do for this is substitute in 2 and 4 and we get 6. So yeah, it's satisfied the equation. It lies on the line. That's sufficient for a show that. Okay, 3C.